Hello everyone, and welcome back to the channel. Today, we're diving deep into a fascinating new paper that could fundamentally change our understanding of quantum mechanics and its relationship with consciousness. The paper is titled The Ontology of Procedural Latency, a formal model for the physical correlates of phenomenal time, and it's authored by Irfan Boko. This work proposes a bold new idea, that the subjective experience of time, what philosophers call phenomenal time, isn't just an illusion created by our brains. Instead, it might be a real, physical process happening at the quantum level. So, what exactly is procedural latency? Imagine you're running a complex computer simulation. The time it takes for the computer to process each step is a real, measurable delay. Boko's paper suggests that something similar happens in quantum systems. He argues that the very process of a quantum state evolving and eventually decohering, that is, losing its quantum properties and behaving like a classical object, takes a finite amount of time. This processing time is what Boko calls procedural latency. The core idea is that this latency isn't just a byproduct. It's the physical basis for our subjective experience of the present moment. It's the physical now. To make this idea testable, Boko introduces a new mathematical framework. The star of the show is a proposed fundamental constant called the Boko constant, represented by the Greek letter tau with a subscript b. The formula for this constant is B equals E. Let's break that down. Alpha is the fine structure constant, a fundamental physical constant that characterizes the strength of the electromagnetic interaction. Or H bar is the reduced Planck constant, a cornerstone of quantum mechanics. And D represents the total energy of the quantum system. This equation is elegant because it connects the proposed duration of a quantum moment directly to fundamental constants of nature and the energy of the system itself. It predicts that for any given quantum system, there's a specific, non-zero amount of time it takes for a quantum event to fully happen. This is a radical departure from standard quantum mechanics, which typically treats state collapse as an instantaneous event. Boko's model suggests it's not instant at all. It's a process with a specific duration defined by this constant. The next piece of the puzzle is something called threshold-gated decoherence dynamics. This sounds complicated, but the concept is quite intuitive. Think of it like a tipping point. According to the paper, a quantum system remains in its pure quantum state, a superposition, for a duration defined by the Boko constant, B. During this period, it's shielded from the environment. However, once this time threshold is reached, a gate opens, and the system rapidly decoheres, interacting with its surroundings and settling into a definite, classical state. To describe this process mathematically, Boko uses a modified master equation. In quantum mechanics, a master equation is a tool used to describe how a quantum system evolves over time, especially when it's interacting with an environment. Boko's version incorporates this time-gated mechanism. It essentially says that for the first period of time, equal to B, there is no decoherence. The system is perfectly isolated. But at the exact moment the timer hits B, decoherence kicks in at a rate determined by the system's coupling to its environment. This creates a distinct, step-like pattern in the system's evolution, which is fundamentally different from the smooth, continuous decay predicted by standard models. Now, this is all fascinating theory, but how can we actually test it? This is where the paper gets really exciting. Boko provides specific, numerical predictions for a real-world quantum system, a 5 GHz transmon qubit. Transmon qubits are one of the leading technologies used in building quantum computers, so they are systems that physicists know how to build and measure with incredible precision. The paper calculates the predicted value of the Boko constant for this specific system. Using the formula B equals E and plugging in the known values for the fine structure constant, the reduced Planck constant, and the energy of a 5 GHz qubit, the model predicts a procedural latency of approximately 1.5 picoseconds. A picosecond is a trillionth of a second, an incredibly short amount of time, but one that is well within the reach of modern experimental techniques. The prediction is clear. If you measure the coherence of a 5 GHz transmon qubit, you should see it remain perfectly stable for the first 1.5 picoseconds, and only after that threshold is crossed should you see the onset of decoherence. This is a sharp, falsifiable prediction. Standard quantum theory, by contrast, predicts that decoherence should begin immediately, although very slowly at first, and follow a smooth exponential decay curve. The two predictions are starkly different. An experiment could therefore be set up to measure the coherence decay of these qubits with ultra-high time resolution. If we see a 1.5 picosecond delay, it's a massive win for Boko's model. If we see a smooth, immediate decay, the model is falsified. The paper goes even further. exploring some of the philosophical implications of this model. One of the most intriguing concepts discussed is the idea of a zombie system. In philosophy, a philosophical zombie is a hypothetical being that is physically and behaviorally indistinguishable from a conscious person but lacks any subjective experience. Boko applies this concept to the quantum realm. A quantum zombie system would be a system that decoheres in the standard, continuous way, without the time-gated latency. Such a system would process information and interact with its environment, but according to the model, it would lack the physical correlate of phenomenal time. It would have no now. We are not zombie systems. This bridges the gap between physics and philosophy, suggesting that the very nature of our subjective reality is written into the laws of quantum mechanics. This idea provides a clear criterion for what makes a system conscious in this physical sense. A system that exhibits procedural latency has the physical grounding for phenomenal experience. A system that doesn't. This is a powerful, if provocative, claim that moves the discussion about consciousness from pure philosophy into the realm of testable physics. Finally, in a move that reflects the modern era of scientific research, the paper includes a detailed acknowledgement of collaboration with artificial intelligence. Irfan Boko explicitly credits 3 different large language models for their specific contributions to the paper. Gemini was used for brainstorming the initial conceptual framework and for exploring the philosophical implications, particularly the concept of zombie systems. ChatGPT was tasked with refining the mathematical formalism and helping to draft the method section, ensuring the descriptions of the master equation and the decoherence dynamics were clear and precise. And Grok was utilized for a literature review and for identifying potential experimental challenges and falsifiability criteria, essentially stress testing the paper's claims against existing knowledge. This is a remarkable example of how AI is becoming a collaborative partner in cutting-edge scientific discovery. It's not just a tool for spell checking. It's a partner in brainstorming, mathematical formulation, and critical analysis. This transparency is incredibly important for the future of science. In summary, Irfan Boko's paper on procedural latency presents a novel, testable, and deeply profound model that connects the quantum world to our subjective experience of time. With its new fundamental constant, specific predictions for quid experiments, and fascinating philosophical ideas like quantum zombie systems, this work has the potential to spark a new wave of research at the intersection of physics, neuroscience, and philosophy. Whether the experiments will confirm or falsify the theory remains to be seen, but the journey to find out will undoubtedly teach us something new about the nature of reality. Thanks for watching. If you found this deep dive interesting, please hit the like button, subscribe for more content on the frontiers of science, and share your thoughts in the comments below. See you next time.